Good morning, dear students. Welcome back to physics class. Today, I would like to present new topic dimensions of physical quantities part A. The subtopics are first one dimensional formulae and dimensional equations and second one dimensional analysis and its applications. This is one of most important topics which one I am going to discuss on today because it determines more weightage mark from chapter 2 for the examination. You should know the nature of a physical quantity is described by its dimensions. If you are asked a question, what are the 7 fundamental or base physical quantities? You can say that they are length, mass, time, electric current, thermodynamic temperature, amount of substances, and the luminous intensity. These base quantities are called as 7 dimensions of the physical world, which are denoted with square brackets. Why are these base quantities called as the 7 dimensions of the physical world? Because all the physical quantities represented by derived units can be expressed in terms of some combinations of 7 fundamental or base quantities. The dimensions of a physical quantity are represented by square brackets around that quantity. For examples, the dimensions of base quantities such as length, mass, time, electric current, thermodynamic temperature, luminous intensity, and amount of substance are represented as shown in this slide. The square bracket around a quantity, which may be a combination of 2 or more base quantities, indicates the dealing with the dimensions of the base quantities. How can we define the dimensions of a physical quantity? The dimensions of a physical quantity are the powers or exponents to which the base quantities are raised to represent that quantity. In mechanics, all the physical quantities can be written in the terms of dimensions, that is, the dimensions of length, mass, and time. For examples, you know that volume of an object V is equal to its length into its breadth into its height. Here, length, breadth, and height are the common 3 lengths. So, its dimension is equal to dimension of L into dimension of L into dimension of L is equal to dimension of L cube is equal to dimension of L cube, which means that 3 dimension in L. Similarly, we can find dimension of force since force is equal to mass into acceleration, as acceleration is equal to velocity divided by time, and also you know that velocity is equal to distance by time. So its dimension can be written as dimension of mass into dimension of acceleration, as dimension of acceleration is equal to dimension of velocity divided by dimension of time, as dimension of velocity is equal to dimension of distance divided by dimension of time, which is equal to dimension of L by dimension of t square or dimension of L t raised to minus 2. So, dimension of force is equal to dimension of mass into dimension of acceleration, which is equal to dimension of m into dimension of L t raised to minus 2, which is equal to dimension of m L t raised to minus 2. The other dimensions for a quantity are always 0. For example, for volume, only length has 3 dimensions, but the mass, time, etc. have 0 dimensions. How can we represent the 0 dimensions of other base quantities in writing the dimension of a physical quantity? It can be understood from the first example only. Dimension of volume is equal to dimension of LQ, which also can be written as dimension of m the power of 0, L the power of 3, T the power of 0, where 0 dimension in mass is represented by dimension of m the power of 0 and 0 dimension in time is represented by dimension of t the power of 0. Let us consider second example. Force F is equal to mass into acceleration m into a. The dimensions of force can be written as dimension of mass into dimension of acceleration is equal to dimension of m into dimension of L divided by dimension of t square is equal to dimension of m L t raised to minus 2, which means that the force has one dimension in mass, one dimension in length and minus 2 dimension in time. The dimensions in all other base quantities are 0. We have not considered the magnitudes of physical quantities by this type of representations because this is only the qualitative analysis but not quantitative. So, the magnitudes of these physical quantities cannot be measured by this kind of representations. For example, consider this list of physical quantities. They are change in velocity, initial velocity, average velocity, final velocity, and speed of objects, which can be expressed as length divided by time. Their dimensions are dimension of L by dimension of t or dimension of L t the power of minus 1. Here, the distance is also the length, even though these physical quantities may have different magnitudes, but their dimensions are the same. On next, I am going to discuss on very important part. They are dimensional formulae and dimensional equations. What are the dimensional formulae and dimensional equations? Dimensional formula is the expression which shows how and which of the base quantities represent the dimensions of a physical quantity. And dimensional equation is an equation which is obtained by equating a physical quantity with its dimensional formula. The dimensional equations represent the dimensions of a physical quantity in terms of the base quantities. Students, it is important to study the dimensional formulae of some important physical quantities in view of your examination. This slide shows a table of some important physical quantities and their dimensional formulae. Four physical quantities, which are volume, speed, force, and mass density, whose dimensional formulae and dimensional equations are given in this slide. First one is volume. Its dimensional formula is dimension of m the power of 0, L the power of 3, T the power of 0. And its dimensional equation is dimension of V is equal to dimension of m the power of 0, L the power of 3, T the power of 0. Second one is speed. Its dimensional formula is dimension of m the power of 0, L, T the power of minus 1. And its dimensional equation is dimension of V is equal to dimension of m the power of 0, L, T the power of minus 1. Third one is force. Its dimensional formula is dimension of m, L, T the power of minus 2, and its dimensional equation is dimension of F is equal to dimension of m, L, T the power of minus 2. And fourth one is mass density. Its dimensional formula is dimension of m, L the power of minus 3, T the power of 0, and its dimensional equation is dimension of rho is equal to dimension of m, L the power of minus 3, T the power of 0. Next discussing subtopic is dimensional analysis. Dimensional analysis shows that only those physical quantities which have same dimensions can be added and subtracted. This principle is called principle of homogeneity of dimensions. According to this, dimension can be multiplied and cancelled like normal algebraic methods. What is the meaning of homogeneity? Homogeneity means those one which are of same kinds. Here, the physical quantities are having homogeneity in nature in case of their dimensions. The dimensions of the physical quantities are the same, so they can be added and subtracted. You also have to note that dimensions of physical quantities can be multiplied and cancelled like normal algebraic methods. For example, distance is equal to speed into time. In dimension terms, dimension of L is equal to dimension of L T the power of minus 1 into dimension of T. Since dimensions can be cancelled like algebra, dimension of T gets cancelled and the equation becomes dimension of L is equal to dimension of L. In mathematical equations, quantities on both sides must always have same dimensions. You have to note this point. Some special functions like trigonometric, logarithmic and ratio of some physical quantities are dimensionless. Next very important part of the chapter is applications of dimensional analysis. What are the applications of dimensional analysis? First application is checking dimensional consistency of equations. The principle of homogeneity of dimensions in an equation is extremely useful in checking the correctness of an equation. A dimensionally correct equation must have same dimensions on both the sides of the equations. If the dimensions of all the terms are not same, the equation is wrong. You also have to remember that a dimensionally correct equation need not be a correct equation, but a dimensionally incorrect equation is always wrong. It can test dimensionally validity but not find exact relationship between the physical quantities. For example, x is equal to x0 plus v0 t plus 1 by 2 at square. When this equation is written in the form of dimension of L is equal to dimension of L plus dimension of L t the power of minus 1 into dimension of t plus dimension of L t the power of minus 2 into dimension of t square, where x be the distance traveled in time t, x0 be the starting position, v0 be is initial velocity, and a be the uniform acceleration. So, dimensions on both sides will be dimension of L as dimension of t gets cancelled out. So, this is a dimensionally correct equation. You have to note these points again. The first one is the special functions such as the trigonometric, logarithmic and exponential function must be dimensionless. And second one is a pure number ratio of similar physical quantities such as angle as the ratio of length to length, refractive index as the ratio of speed of light in vacuum to speed of light in medium, etc. has no dimensions. And second application is deducing relation among physical quantities. Dimensional analysis can be useful to deduce relation among the physical quantities. To deduce the relation among the physical quantities, we should know the dependence of one physical quantity over others or independent variables and consider it as the product type of dependence. But this has a limitation. Dimensionless constants cannot be obtained using this method. For example, to derive the expression t is equal to k root of L by g. Here root is for L and g. Assume there is a relation among t, L, m and g which can be mathematically written as t is proportional to L the power of x, g the power of y, m the power of z. So, t is equal to a constant k into L the power of x, g the power of y, m the power of z. This is the equation number 1. Or, in the form of dimension, the assumed relation can be written as dimension of L the power of 0, m the power of 0, t the power of 1 is equal to dimension of L the power 1 whole raised to x into dimension of L the power of 1 t the power of minus 2 whole raised to y into dimension of m the power of 1 whole raised to z is equal to dimension of L the power of x plus y, t the power of minus 2y, m the power of z. Then dimension of L the power of 0, m the power of 0, t the power of 1 is equal to dimension of L the power of x plus y, t the power of minus 2y, m the power of z, which means that x plus y is equal to 0, which is the equation number 2, minus 2y is equal to 1, which is the equation number 3, and z is equal to 0, which is the equation number 4. Here, equated their powers or exponents So we will get x is equal to 1 by 2 from the equations 2 and 3. Y is equal to minus 1 by 2 from the equation 3 and z is equal to 0 from the equation 4 itself. Remember that the constant k is dimensionless, so it has Ncert. So the original equation reduced to t is equal to k root of L by g. From the equation 1, t is equal to k into L the power of x, g the power of y, m the power of z is equal to k into L the power of 1 by 2, g the power of minus 1 by 2, m the power of 0. Here we have substituted the values of x, y and z in the equation. So it is obtained as k L the power of 1 by 2, g the power of minus 1 by 2, m the power of 0. It is equal to k L the power of 1 by 2, g the power of minus 1 by 2 is equal to k L the power of 1 by 2 divided by g the power of 1 by 2 is equal to k root of L by g. Hence, we have got the relation t is equal to k root of L by g. This is the way by which we have derived the expression by using the dimensional analysis. Dear students, today's homework questions are given in this slide. Please, you have to work out these question answers by today itself. Okay, thank you. Have a nice day.